Welcome to the Scientific Nap, a calm space for sleep, stories, and stillness. Let go of the day and drift into rest. Asterisk: when the universe begins, it is dense, hot, and opaque. Roughly 13.8 billion years ago, all the energy and matter that now forms galaxies, stars, planets, and life itself is compressed into an incredibly small, hot region. As the universe expands, it cools. Within the first few minutes, protons and neutrons combine to form the simplest atomic nuclei, mostly hydrogen and helium. In these first moments, light cannot travel freely. The universe is like a thick fog, filled with particles that scatter photons in every direction. For about 380,000 years, this dense plasma keeps light trapped. Gradually, as expansion continues, temperatures drop enough for electrons to combine with atomic nuclei. At this point, neutral atoms form, and the universe becomes transparent for the first time. This moment is called recombination. With the charged particles bound into neutral atoms, photons can finally travel vast distances without constant scattering. The light released then is what scientists today call the cosmic microwave background, or CMB. It is the oldest observable light in the universe, a faint echo of that ancient time, stretched and cooled as the universe expands. The CMB is not visible to human eyes, because its light now falls in the microwave range of the electromagnetic spectrum. Yet it surrounds Earth and every galaxy, filling all of space like a backdrop. When scientists first detected this glow in the 1960s, they confirmed a major prediction of the Big Bang Theory. Arno Penzias and Robert Wilson, working with a radio antenna, noticed a persistent noise they could not explain. After ruling out all possible local sources, they realized they were hearing the faint whisper of the universe's first light. Since then, satellites such as COBE, WMAP, and the Planck spacecraft have mapped the CMB in remarkable detail. These maps show tiny variations in temperature and density, patterns that reveal where matter was slightly denser or thinner than average. These early fluctuations are critical. They act as seeds for all later cosmic structures. Over billions of years, gravity amplifies these slight differences, gathering matter into the galaxies and clusters visible today. The CMB's uniformity is striking but not absolute. The temperature across the sky is about 2.7 Kelvin, just above absolute zero, but varies by mere millionths of a degree. These small temperature shifts help cosmologists estimate the universe's age, shape, and contents. For instance, they show that normal matter, the atoms that make up stars, planets, and people, is only a small part of the cosmos. Dark matter and dark energy account for most of the total mass energy content. Studying the CMB also tests models of cosmic inflation. This theory suggests that the universe expanded exponentially fast in the first tiny fraction of a second, smoothing out any large-scale irregularities. Inflation explains why the CMB looks nearly the same in every direction. It also predicts the specific pattern of fluctuations that telescopes observe. Observations of the CMB continue to improve with new instruments on Earth and in space. Scientists now study the polarization of this ancient light, the slight alignment of its waves, to probe subtle features of the early universe. Polarization patterns can offer clues about primordial gravitational waves, which are ripples in spacetime that inflation may have produced. The CMB is more than just a snapshot of the infant universe. It is a powerful tool for measuring cosmic Expansion. By comparing the CMB's features with the distribution of galaxies today, researchers can test how the universe has changed over billions of years. This helps refine estimates for the Hubble constant, the rate at which the universe expands. Yet precise measurements sometimes reveal tensions. For example, the Hubble constant inferred from the CMB does not exactly match the value measured. Using nearby galaxies and supernova, scientists explore whether this mismatch hints at new physics beyond the standard model of cosmology. Instruments like the South Pole Telescope and the Atacama Cosmology Telescope extend this work, scanning the sky for even finer details in the microwave background. Future missions may uncover more about the nature of dark matter, dark energy, or other unknown components influencing cosmic evolution. All this knowledge comes from faint, cold light that has traveled for nearly 14 billion years. Every photon in the CMB has crossed vast stretches of expanding space, carrying a message from an era long before stars or galaxies formed. This ancient radiation remains one of astronomy's clearest windows into the universe's beginning. By tracing this light, scientists learn how the universe evolved from a hot, dense plasma to a structured cosmos. They see how tiny quantum fluctuations grew into immense galaxies and clusters. They test theories that reach back to fractions of a second after the Big Bang. As new telescopes refine the view, the CMB continues to answer and raise fundamental questions about the universe's origin and fate. What it reveals guides researchers to the next puzzles waiting in the darkness. Among them is how the matter that formed galaxies came together and what invisible forces shaped it. Gravity provides the answer. In the early universe, slight differences in the density of matter pull particles together under their mutual attraction. Over time, these tiny overdense regions gather more material, growing into larger and larger clumps. As these clumps expand, they form the earliest cosmic structures, the building blocks of galaxies. Dark matter plays a crucial role in this process. Although invisible, it makes up most of the universe's mass and interacts through gravity. Dark matter gathers into vast, invisible halos, drawing in ordinary gas through its gravitational pull. Inside these halos, gas cools and condenses, forming the first stars and clusters. The first galaxies emerge about 400 million years after the Big Bang. They are smaller than today's large galaxies, more like compact, irregular clouds of stars and gas. As galaxies collide and merge, they grow in size and complexity. This merging continues for billions of years, shaping galaxies into the spirals, ellipticals, and irregular forms observed today. Stars within galaxies form when cold gas collapses under gravity. Dense clouds of hydrogen and helium fragment into clumps, each clump becoming a nursery for new stars. In these stellar nurseries, radiation and winds from young stars can trigger more star formation nearby or push gas away, regulating how quickly a galaxy makes new stars. Supernova explosions contribute to when massive stars end their lives in spectacular blasts. They eject heavy elements into surrounding space. This enriches the gas with elements like carbon, oxygen, and iron, which future generations of stars and planets need to form. Supernova also stir and heat the gas, influencing how it flows through a galaxy. Black holes, especially the supermassive ones at galaxy centers, shape galactic evolution on a grand scale. These black holes can contain millions or even billions of times the sun's mass. As gas and stars spiral inward, they feed the black hole, causing it to emit powerful radiation and jets of energetic particles. This energy can heat or expel gas, slowing new star formation and affecting the galaxy's future growth. The Milky Way offers a clear example of these processes. This galaxy, home to the Sun and its planets, is a barred spiral with a disk of stars, gas, and dust arranged in sweeping arms. At its center lies a supermassive black hole called Sagittarius A*. Although quiet today, this black hole likely shaped the Milky Way's core during its more active phases. The Milky Way's disk is not alone. Surrounding it are small satellite galaxies and streams of stars, remnants of past mergers. Some of these satellites, like the large and small Magellanic Clouds, still orbit nearby, slowly losing stars and gas to the Milky Way's gravity. Astronomers study galaxies across billions of light years to understand how they change over cosmic time. By observing distant galaxies, they see snapshots of the past. Some appear chaotic and clumpy, showing vigorous star formation and frequent collisions. Others already show ordered structures like disks and bulges. Modern telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, reveal details about young galaxies and their evolution. By measuring light at different wavelengths, scientists detect how much gas they hold, how fast stars form, and how central black holes grow. Simulations also help. Supercomputers model billions of particles representing dark matter and gas, tracking how gravity pulls them together. These simulations test how well theories match real observations. They show how cosmic structures grow from small clumps to galaxy clusters bound by vast webs of dark matter. Galaxies do not evolve in isolation. They live in clusters and groups, bound by gravity. In these crowded environments, galaxies interact, sometimes stripping gas from each other or merging entirely. These interactions trigger new bursts of star formation or fuel central black holes, changing the galaxy's shapes and star-making activity. Different types of galaxies reflect these histories. Spiral galaxies like the Milky Way have disks with active star formation. Elliptical galaxies, often found in dense clusters, have little cold gas left and mostly old stars. Their smooth shapes suggest they formed through repeated mergers, which mixed their stars into larger, rounded systems. Irregular galaxies, meanwhile, often show distorted shapes. Tidal forces from neighbors or past collisions can stretch and twist their stars and gas, leaving behind bridges, tails, and scattered clusters. These forms highlight how dynamic and changing the universe remains. Even now, galaxies keep changing. The Milky Way is on course to merge with the Andromeda Galaxy in about 4 billion years. When this happens, their stars and black holes will combine, reshaping both galaxies into a larger elliptical or lenticular form. This cycle of growth through mergers and star formation continues, powered by gravity and the hidden scaffolding of dark matter. All of this shows how small differences in the early universe's density lead to the rich diversity of galaxies seen. Today, gravity turns tiny seeds into vast islands of stars and gas, structured by invisible dark matter and shaped by starbirth, explosions, and black holes. The Milky Way, like countless other galaxies, carries this history in its structure and motion. Its spiral arms, star clusters, gas clouds, and dark halo all reveal clues about billions of years of cosmic evolution. Yet, despite all that is known, questions remain. What exactly is dark matter made of? How do supermassive black holes grow? So large, so early. How does star formation shut down in some galaxies but flourish in others? Evidence for dark matter appears first in the motion of galaxies. In the 1970s, astronomer Vera Rubin studied how stars orbit within spiral galaxies. She and her colleagues measure how fast stars move at different distances from a galaxy's center. According to the laws of gravity, stars farther from the center should move more slowly because less visible mass lies beyond them to pull them inward. Yet Rubin finds something surprising. Stars on the outskirts orbit just as quickly as those closer in. This observation does not fit with the amount of visible matter alone. If only stars, gas, and dust were present, the outer regions should drift apart. The steady rotation suggests there is much more mass than telescopes can see. An unseen halo envelops each galaxy, providing the extra gravity needed to hold stars in place. This invisible mass becomes known as dark matter. It does not emit, absorb, or reflect light, making it impossible to detect directly. Its presence is revealed only through its gravitational influence on visible objects. Another clue comes from galaxy clusters. In the 1930s, Fritz Zwicky studied the Coma Cluster, a massive gathering of galaxies. He calculates how much mass is needed to keep the galaxies bound together given their high speeds. The result shows far more mass than the light from stars. Accounts for Zwicky calls the missing mass Dunkel Materie, or dark matter. At first, the idea draws little attention. But later, measurements confirm his conclusion. Galaxy clusters contain huge amounts of unseen matter. Gravitational lensing provides further proof. According to Einstein's theory of general relativity, massive objects bend the path of light passing nearby. When a cluster of galaxies sits between Earth and a more distant galaxy or quasar, its gravity acts like a lens, distorting and magnifying the background light. By studying these distortions, astronomers can map how much mass sits in the foreground cluster. Again, the visible matter alone is not enough. Only with dark matter do the gravitational effects match the observations. Dark matter is also critical for explaining the cosmic web, the large-scale structure of the universe. Simulations show that visible matter alone cannot clump into galaxies and clusters as observed. Dark matter acts as scaffolding, forming vast filaments and halos where gas can cool and form stars. Without dark matter, galaxies like the Milky Way would not have had enough gravitational pull to grow as they did, though its presence is widely accepted. The true nature of dark matter remains one of science's biggest mysteries. Many theories propose that dark matter consists of unknown particles that rarely interact with normal matter except through gravity. Candidates include WIMPs, weakly interacting massive particles, which could pass through ordinary matter without leaving a trace. Another idea suggests X-ions, extremely light particles that could be abundant yet invisible. To search for these particles, physicists build experiments deep underground, shielded from cosmic rays and other background noise. Detectors use tanks of liquid xenon, ultra-cold crystals, or supersensitive sensors, hoping that once in a while a dark matter particle might collide with an atomic nucleus and create a tiny measurable signal. Astronomers also look to the sky for hints. If dark matter particles sometimes annihilate or decay, they could produce gamma rays or other particles. Observatories like the Fermi Gamma Ray Space Telescope scan regions with high dark matter concentration, such as the centers of galaxies, for unexplained signals. So far, no conclusive detection has appeared. Meanwhile, alternative explanations challenge whether dark matter particles are necessary at all. Some theories propose modifications to gravity at large scales, suggesting that the laws of gravity might behave differently in regions with very low acceleration. These ideas, such as modified Newtonian dynamics, MOND, remain debated but have not replaced the dark matter hypothesis, which matches observations across many scales. Despite the mystery, dark matter shapes nearly every large structure in the universe. Without it, galaxies would fly apart, galaxy clusters would dissolve, and the cosmic web would not exist in its present form. Dark matter's gravitational pull binds the visible universe together. Astronomers map dark matter indirectly, by observing how it bends light or affects the motion of galaxies. These maps reveal vast halos around individual galaxies, bridges of dark matter linking galaxy clusters, and dense knots where dark matter gathers at intersections of cosmic filaments. The study of dark matter pushes the limits of technology and theory. Future experiments aim to detect possible dark matter particles directly, while large telescopes and space missions refine how its gravity shapes the cosmos. Projects like the Vera C. Rubin Observatory will survey billions of galaxies to measure how dark matter bends light over vast distances, offering more clues about its distribution. Each new observation brings the scientific community closer to understanding what makes up this hidden mass. If researchers can detect or create dark matter particles in the lab, or uncover clear signatures in cosmic rays, they may answer one of modern science's most pressing questions. Yet, the universe holds another mystery alongside dark matter. Observations show that the cosmos is not just held together by invisible mass, it is also expanding faster and faster. Something unseen drives this acceleration and adds another hidden layer to the cosmic story. The discovery of dark energy begins with the careful study of distant supernova. In the late 1990s, two independent teams of astronomers examined type Ia, supernova powerful explosions that occur when a white dwarf star pulls in too much matter from a companion star. These explosions always reach nearly the same peak brightness, making them reliable cosmic yardsticks. By comparing how bright these supernova appear from Earth, astronomers estimate their distance. By measuring their redshift, the stretching of light to longer wavelengths, they determine how fast the galaxies containing them move away. When the teams analyzed dozens of supernova billions of light years away, the results surprised them. Instead of slowing down, as expected if gravity alone were acting, the expansion of the universe appears to be speeding up. Something unknown works against gravity, pushing galaxies apart faster over time. This repulsive effect is given the name dark energy. It does not refer to a specific particle or force yet, but rather to whatever accounts for this observed acceleration. Dark energy makes up about 68% of the total energy content of the cosmos, vastly outweighing normal matter and even dark matter. Other lines of evidence support this idea. The cosmic microwave background shows patterns that match a universe dominated by dark energy. Maps of galaxies and clusters reveal how large-scale structures grow more slowly than they would in a purely matter-filled universe. These observations point to an energy component that resists gravitational pull and drives space to stretch more quickly. Einstein's equations of general relativity allow for such a phenomenon. In 1917, he introduced a cosmological constant to balance the pull of gravity and keep the universe static, a concept he later calls his biggest blunder when expansion is discovered. Yet this constant represented by the Greek letter lambda. Lambda fits perfectly as one possible form of dark energy. In this model, the cosmological constant acts as a property of space itself, adding energy uniformly across the cosmos. However, the true nature of dark energy remains uncertain. Some theories suggest that dark energy could change over time, unlike a constant value. A dynamic version, called quintessence, would act like a field-filling space with properties that shift slowly. Scientists test these ideas by observing ever more distant supernovae and mapping how structures, like galaxy clusters, spread through time. Another tool for probing dark energy is the study of baryon acoustic oscillations. These are subtle patterns in how galaxies cluster on large scales, a leftover imprint from sound waves traveling through the hot plasma of the early universe. By measuring how these patterns appear at different distances, astronomers track how expansion has changed, providing clues about dark energy's behavior. Gravitational lensing also adds insight. By watching how massive structures bend light from background galaxies, scientists map the distribution of dark matter and examine whether dark energy affects how these structures grow and cluster. Despite decades of research, no direct detection of dark energy exists. It does not appear to interact with matter or light in any way other than through gravity's equations. This elusiveness pushes researchers to develop new experiments and telescopes, aiming to tighten measurements of cosmic expansion and structure. Future observatories like the Euclid spacecraft and the Nancy Grace Roman Space Telescope are designed to survey millions of galaxies. They will measure distances, redshifts, and the shapes of galaxy clusters to refine the expansion history of the universe. The hope is that small deviations from the simplest models might reveal hints about the true nature of dark energy. The effect of dark energy shapes the long-term fate of the cosmos. If it remains constant or grows stronger, the universe will keep expanding forever, with galaxies drifting farther apart until stars burn out and matter spreads thin. Some models predict an ultimate big freeze, where cosmic temperatures drop toward absolute zero. Other, more speculative ideas suggest a big rip, where dark energy's push becomes so strong that it tears apart galaxies, stars, and even atoms in the distant future. Still, some questions remain. Could dark energy weaken over time, allowing gravity to slow expansion again? Might new physics beyond Einstein's theory explain the acceleration without invoking an unknown energy? Researchers test these ideas by comparing models with precise measurements of cosmic microwave background radiation, galaxy surveys, and distant supernova. Even today, the mystery of dark energy drives the design of telescopes, space missions, and experiments. It connects fundamental physics to observations of the largest scales. Unlocking its secrets may also reveal new aspects of quantum fields, gravity, or hidden dimensions. While dark energy shapes the cosmos on the largest scales, stars remain the engines of creation within galaxies. They fuse simple elements into heavier ones, recycle matter through explosions, and light up the sky with energy born in their cores. To understand how the universe's ingredients change and grow, it is necessary to look closely at how stars form, live, and die. The answer begins deep inside the cores of stars, where temperatures and pressures reach extraordinary levels. In these conditions, hydrogen atoms, the simplest and most abundant element, fuse together through nuclear fusion. This process converts hydrogen into helium, releasing tremendous amounts of energy in the form of light and heat. This energy pushes outward, balancing the inward pull of gravity and allowing a star to remain stable for millions or even billions of years. Fusion inside. Stars starts when clouds of gas and dust collapse under their own gravity. These vast clouds, called nebulae, contain mostly hydrogen with traces of helium and heavier elements left behind by earlier generations of stars. As the gas contracts, it heats up. When the core temperature reaches about 10 million degrees Celsius, hydrogen nuclei move fast enough to overcome their mutual repulsion and fuse. This fusion process powers stars like the Sun. In the Sun's core, about 600 million tons of hydrogen fuse into helium every second. The energy from these reactions travels outward, taking thousands of years to pass through the dense inner layers before radiating into space as sunlight. Stars of different masses live very different lives. Small stars, known as red dwarfs, burn their hydrogen fuel slowly and can shine for trillions of years. Larger stars consume fuel much faster and have much shorter lifespans. A star with several times the Sun's mass might exhaust its core hydrogen in just a few million years. When hydrogen in a star's core runs out, gravity takes over again, compressing the core until it heats enough to ignite helium fusion. In this next stage, helium atoms fuse to form heavier elements like carbon and oxygen. In massive stars, this cycle continues. The core contracts and heats repeatedly, fusing heavier and heavier elements up to iron. Iron is a turning point. Fusion reactions that produce elements lighter than iron release energy, but fusing iron or heavier elements requires energy instead of releasing it. When a massive star's core fills with iron, fusion stops supporting the core against gravity. The core collapses within seconds, triggering a spectacular explosion known as a supernova. A supernova blasts outer layers into space, scattering newly forged elements across the galaxy. The extreme heat and energy of the explosion also create elements heavier than iron, such as gold, uranium, and platinum. These precious and rare elements form only in the final moments of a massive star's life or through the collision of neutron stars. Another violent cosmic event. Stars not massive enough to go supernova follow a gentler path. When they exhaust their fuel, they shed outer layers and leave behind a dense, hot core called a white dwarf. Over billions of years, this remnant cools and fades. Even so, these stars contribute to the cosmic supply of carbon, nitrogen, and other life-essential elements by enriching surrounding space with gas during their final stages. The matter released by dying stars mixes with existing interstellar gas. This enriched material becomes part of new generations of stars and planets. Every atom of oxygen in Earth's atmosphere, the carbon in living cells, and the iron in blood and rocks once formed in the cores of stars or during supernova explosions. The Sun, like other middle-sized stars, sits halfway through its stable life. It formed about 4.6 billion years ago from a cloud enriched by earlier generations of stars. In roughly 5 billion more years, it will expand into a red giant as it burns through its remaining hydrogen and helium. Eventually, it will shed its outer layers, creating a glowing shell of gas called a planetary nebula, leaving a white dwarf at the center. Astronomers study the life cycles of stars by observing them in all stages of development. Young stellar nurseries reveal newborn stars still gathering mass. Mature stars, like the Sun, show stable fusion in action. Older stars and supernova remnants demonstrate how material returns to space. Instruments detect the light from fusion reactions, the shock waves of stellar winds, and the chemical fingerprints of different elements. Through this cycle of birth, fusion, and death, stars shape the chemical makeup of galaxies. They recycle matter, making each new generation richer in elements heavier than hydrogen and helium. Without this constant renewal, planets like Earth with rocky surfaces, water, and the building blocks for life could not exist. Stars also influence their surroundings through intense radiation and powerful winds. Massive young stars carve cavities in their birth clouds, triggering new rounds of star formation nearby. Supernova shockwaves compress surrounding gas, encouraging further collapse and seeding the next stellar generation. In this way, stars act as both creators and catalysts. They transform simple elements into complex ones and help spread these materials throughout the universe. This stellar alchemy connects the life cycles of stars to the history of planets, atmospheres, and life itself. Still, some stars leave behind more than gas and dust. When massive stars collapse, they can form black holes, regions of space where gravity is so strong that not even light escapes. These black holes, large and small, add another layer to the cosmic story of matter and energy. When a massive star reaches the end of its life, its core can no longer produce the outward pressure needed to resist gravity. If the core's mass is large enough, typically more than about 3 times the mass of the Sun, no known force can stop the collapse. The core compresses under its own gravity until it forms a black hole, an object so dense that nothing, not even light, can escape its pull. At the center of a black hole lies a point called a singularity, where matter is crushed to infinite density. Surrounding it is the event horizon, the boundary beyond which nothing can return. The event horizon marks the limit where escape velocity exceeds the speed of light. Anything crossing this boundary, gas, dust, light, or even entire stars, disappears from view, leaving only its gravitational influence behind. Black holes vary widely in size. Stellar mass black holes form from collapsing stars and range from a few to dozens of solar masses. Supermassive black holes, millions or billions of times more massive than the Sun, sit at the centers of most large galaxies. How these enormous black holes grow so large is an open question. They may form from the merging of smaller black holes or by feeding on vast amounts of gas over cosmic time. Although black holes themselves emit no light, astronomers detect them through their effects on nearby matter. When a black hole pulls in gas from a companion star or a surrounding disk, the gas spirals inward, forming an accretion disk. Friction and gravitational energy heat the disk to extreme temperatures, causing it to emit X-rays and other radiation. Observatories detect this high-energy light, revealing the presence of the invisible object. The first confirmed black hole, Cygnus X1, was discovered this way. In the 1960s, scientists detected intense X-rays from a bright star paired with an unseen, massive companion. Calculations showed that the invisible partner's mass was too great to be a neutron star, pointing to a black hole. Another method for detecting black holes is to watch how their gravity bends light. When a black hole passes in front of a distant star or galaxy, its gravity can magnify and distort the background light, a phenomenon known as gravitational lensing. This effect, predicted by Einstein's theory of general relativity, allows astronomers to detect black holes that might otherwise remain hidden. One of the most striking achievements in black hole research came in 2019, When the Event Horizon Telescope collaboration released the first image of a black hole's shadow. Using a global network of radio telescopes, scientists captured the silhouette of the supermassive black hole in the galaxy M87. The image shows a dark center surrounded by a bright ring of glowing gas, heated as it spirals toward the event horizon. Black holes do not just swallow matter, they also shape their surroundings. When gas falls into a supermassive black hole, some material does not cross the event horizon immediately. Instead, powerful jets of particles can blast out at nearly the speed of light, extending far beyond the host galaxy. These jets carry enormous energy, influencing how gas cools and forms stars in the galaxy. By regulating the flow of matter, black holes help determine how galaxies evolve over billions of years. The Milky Way's own supermassive black hole, called Sagittarius A*, has a mass of about 4 million suns. Although relatively quiet today, evidence shows that it was once more active, producing energetic outbursts that shaped the central region of the galaxy. Observations of stars orbiting Sagittarius A* provide precise measurements of its mass and confirm that it must be a black hole. Black holes also serve as cosmic laboratories for testing the laws of physics under extreme conditions. Near a black hole's event horizon, gravity becomes so intense that time and space behave differently. Time slows down near the horizon compared to a distant observer, an effect confirmed by studying the orbits of stars and gas near supermassive black holes. The study of black holes has expanded further with the detection of gravitational waves, ripples in space-time caused by massive objects moving rapidly. In 2015, the LIGO Observatory made the first direct observation of gravitational waves, produced by the collision and merger of two black holes billions of light-years away. Since then, dozens of such events have been recorded, providing new insights into how black holes form, merge, and grow despite their reputation for swallowing everything nearby. Black holes can gradually evaporate through a process called Hawking radiation, named after physicist Stephen Hawking. This theoretical effect suggests that black holes can emit tiny amounts of radiation due to quantum effects near the event horizon. Over unimaginably long timescales, small black holes could eventually vanish completely, but this process remains unconfirmed by direct observation. Black holes remain among the universe's most fascinating and extreme objects. They reveal how gravity can shape matter and energy at scales far beyond everyday experience. By studying them, scientists test the limits of current theories, exploring where general relativity and quantum mechanics might intersect. Yet even these powerful cosmic objects are only part of the story. Many black holes grow by feeding on disks of gas and dust. Understanding how these disks form, how they feed stars and black holes, and how they shape the birth of new stars, leads to another crucial component of cosmic evolution. These disks, known as protoplanetary disks, form around young stars during the early stages of star formation. As a cloud of gas and dust collapses under gravity to create a new star, leftover material settles into a rotating disk. Within this disk, tiny grains of dust collide and stick together, gradually building larger clumps. Over thousands to millions of years, these clumps grow into planetesimals, the building blocks of planets, inside these swirling disks. Complex processes shape the formation of entire planetary systems. Near the young star, heat drives lighter elements away, leaving heavier rocky materials behind. Farther out, cooler temperatures allow ice to remain solid, providing more raw material for larger planets. This temperature difference explains why rocky planets like Earth and Mars form closer to their stars, while gas giants like Jupiter and Saturn emerge in colder, more distant regions. Once planets form, they interact with the disk and each other, sometimes migrating inward or outward. This movement reshapes the system, creating diverse arrangements that differ greatly from the solar system. Observations show that planetary migration can send giant planets spiraling close to their stars, or eject smaller worlds entirely. Until the 1990s, the existence of planets around other stars remained unconfirmed. The first exoplanets discovered orbit a pulsar, a rapidly spinning neutron star, where extreme conditions make life unlikely. Soon after, astronomers find planets around sun-like stars, opening a new era in astronomy. Detecting these distant worlds is challenging because planets are faint compared to their bright host stars. Most exoplanets are found indirectly, using two main techniques: the radial velocity method and the transit method. The radial velocity method measures tiny wobbles in a star's motion caused by the gravitational tug of an orbiting planet. As a planet orbits, it pulls its star slightly toward and away from Earth, shifting the star's light in a pattern that reveals the planet's presence, mass, and orbit. The transit method detects exoplanets when they pass in front of their stars, causing a slight but measurable dimming of the star's light. By observing these dips in brightness, astronomers estimate a planet's size, orbital period, and sometimes its atmosphere. NASA's Kepler Space Telescope, launched in 2009, transformed exoplanet science using the transit method. Kepler monitored more than 150,000 stars, discovering thousands of exoplanets. These discoveries include hot Jupiters, gas giants orbiting extremely close to their stars, as well as rocky, Earth-sized planets in the so-called habitable zone, where temperatures might allow liquid water to exist. Some of the most intriguing worlds are super-Earths, planets larger than Earth but smaller than Neptune. These planets do not exist in the solar system but appear common in the galaxy. Their diversity suggests that planetary systems can differ widely in size, composition, and arrangement. Exoplanet discoveries also include rogue planets, planets not bound to any star, drifting alone through the galaxy. These lonely worlds likely formed in disks, but were rejected by gravitational interactions with larger planets or passing stars. A key goal in exoplanet science is to find potentially habitable worlds. Astronomers search for rocky planets at the right distance from their stars, where temperatures allow water to remain liquid. The TRAPPIST-1 system, for example, has 7 Earth-sized planets orbiting a small, cool star, with several in the habitable zone. Detecting atmospheres is another frontier. When a planet transits its star, some starlight passes through the planet's atmosphere, leaving subtle chemical fingerprints. By studying these signals, scientists search for gases like water, vapor, methane, or oxygen, possible indicators of conditions suitable for life. The James Webb Space Telescope, launched in 2021, expands this search. Its powerful instruments can analyze exoplanet atmospheres in greater detail, looking for signs of clouds, weather, or molecules related to life processes. Exoplanet discoveries reveal that planetary systems are more varied than once imagined. Some stars have tightly packed systems with multiple planets orbiting closer than Mercury does to the Sun. Others host massive planets far from their stars, challenging ideas about how planets form and migrate. Studying exoplanets helps astronomers understand the solar system's history, too. By comparing other systems, scientists test theories about why Earth's neighborhood looks the way it does. The diversity of worlds shows that planet formation is a common outcome of star birth, with countless variations shaped by initial conditions, disk properties, and gravitational interactions. Future missions, like the Nancy, Grace Roman Space Telescope, and new ground-based observatories, will hunt for even more exoplanets. Advanced techniques aim to directly image planets by blocking their host star's light, allowing scientists to study surface features and climate patterns. One day, finding a planet with signs of life may become possible, providing answers to one of humanity's oldest questions: is Earth unique, or is life common among the stars? Yet even as scientists search for distant Earth-like worlds, understanding our own solar neighborhood remains essential. The planets and moons nearby offer clues about how life might arise elsewhere. Clues about life's potential begin far from Earth, within the cold, dark regions of interstellar space. In these vast clouds of gas and dust, known as molecular clouds, atoms combine into simple molecules under low temperatures and gentle radiation. Hydrogen, carbon, oxygen, and nitrogen, the primary elements in organic chemistry, bond into compounds like water, methane, ammonia, and carbon monoxide. Over time, these simple molecules attach to tiny grains of dust, forming icy coatings. Cosmic rays and ultraviolet light from nearby stars trigger chemical reactions in these ices, producing more complex organic molecules. Amino acids, which are the building blocks of proteins, and simple sugars, can form under these conditions. Laboratory experiments on Earth confirm that ultraviolet light acting on icy grains can create molecules relevant to life's chemistry. Comets and asteroids preserve these ancient materials. In the early solar system, leftover debris from planet formation included countless comets in the outer regions and rocky asteroids closer to the Sun. Comets are particularly rich in ices and organic compounds, like time capsules of the primordial ingredients that existed when the planets formed. When these objects collide with young planets, they deliver water and organic compounds to their surfaces. This idea, known as panspermia in its broader sense, suggests that comets and asteroids may have supplied early Earth with key components needed for life to emerge. Meteorites provide direct evidence of this process. Some meteorites that fall to Earth contain amino acids, hydrocarbons, and other carbon-based molecules. The famous Murchison meteorite, which landed in Australia in 1969, contains over 70 types of amino acids, many of which do not naturally occur on Earth. Chemical analysis shows that these compounds formed in space before the solar system finished assembling. Space missions have confirmed that these building blocks remain widespread. The European Space Agency's Rosetta mission, which orbited and landed a probe on Comet 67P Churyumov-Gerasimenko, detected organic molecules like glycine, an amino acid, and phosphorus, a key element for DNA and cell membranes. NASA's Stardust mission captured dust from Comet Wild 2, returning samples containing amino acids and complex hydrocarbons. These discoveries indicate that the ingredients for life's chemistry are not unique to Earth. Instead, they appear naturally in many parts of the cosmos. When planets form within disks of gas and dust, they inherit these chemicals, providing raw material for more complex chemistry once conditions allow liquid water and energy to drive reactions. Moons within the solar system also preserve hints of how organic molecules spread. Saturn's moon, Enceladus, for example, has an icy crust covering a liquid ocean. Plumes of water vapor and ice particles erupt through cracks in the surface, carrying organic molecules into space. NASA's Cassini spacecraft flew through these plumes and detected simple organics and evidence for chemical energy sources that could support life. Jupiter's moon Europa, with its hidden ocean beneath an icy shell, shows signs of possible interactions between water, rock, and organic compounds. These interactions resemble processes that occur at hydrothermal vents on Earth's ocean floor, where life thrives in the dark, fueled by chemical energy rather than sunlight. Studying these moons helps scientists test theories about how life's chemistry starts and spreads. If the necessary molecules are common on icy worlds in our own solar system, they might exist in similar environments orbiting other stars. On Earth, life's early emergence suggests that once conditions become stable enough, organic molecules can organize into more complex structures like proteins and nucleic acids. Energy sources such as sunlight, lightning, and underwater heat provide the spark for these reactions. The first living cells may have formed in warm, mineral-rich environments like hydrothermal vents or shallow ponds, where concentrations of molecules could build up. The story of life's beginnings connects planetary formation, cosmic chemistry, and the transport of organic material across space. By comparing Earth's record to what is found on comets, asteroids, and moons, scientists build a clearer picture of how the raw materials of life assemble naturally in space and arrive on worlds, where they might evolve into living systems. Future missions aim to bring back more samples from primitive bodies. NASA's OSIRIS-REx mission collected material from asteroid Bennu and returned it to Earth for analysis. These samples may contain complex, organic compounds that deepen our understanding of the chemical pathways that lead from simple molecules to life's first steps. Exploring how life's building blocks form and spread in space raises the next question: how do these molecules organize into self-replicating systems? Understanding this transition could reveal whether life is an inevitable outcome wherever conditions are right, or if it remains a rare event. Answering this question begins with the solar system's early history, when the Sun formed from a collapsing cloud of gas and dust about 4.6 billion years ago. The leftover material flattened into a rotating protoplanetary disk. Within this disk, countless grains of dust stuck together, forming clumps that gradually grew into larger bodies called planetesimals. These planetesimals collided and merged under gravity, building up the cores of the planets. In the inner solar system, closer to the Sun, temperatures were too high for water and volatile gases to condense. So rocky planets like Mercury, Venus, Earth, and Mars formed mostly from metals and silicates. Farther out, in colder regions, ice could remain solid, allowing gas giants like Jupiter and Saturn to form. Their massive cores attracted thick envelopes of hydrogen and helium from the disk. Beyond the gas giants, smaller icy worlds and leftovers accumulated in regions known today as the Kuiper Belt and the Oort cloud. Closer in, between Mars and Jupiter, the asteroid belt marks another region of leftover material that never coalesced into a planet, likely due to Jupiter's strong gravitational influence disrupting the process. These leftover regions hold clues about the solar system's hidden history. The asteroid belt contains remnants of the rocky material from the inner disk, while the Kuiper Belt preserves icy bodies that formed in the outer disk. Studying these objects provides a record of the solar system's birth conditions and the chemical ingredients available when Earth and its neighbors formed. meteorites that fall to Earth often come from collisions within the asteroid belt. These space rocks contain some of the oldest material in the solar system, including tiny mineral grains that predate the Sun. By examining their composition, scientists learn about the temperatures, pressures, and chemical reactions that shaped the disk in its earliest days. The Kuiper Belt, which begins just beyond Neptune, includes dwarf planets like Pluto and Eris, along with countless smaller, icy bodies. These distant objects reveal how the outer solar system evolved. Some Kuiper Belt objects have highly elliptical orbits, suggesting they were scattered by Neptune's migration outward in the solar system's early years. Planetary migration reshaped the entire solar system. Models show that Jupiter and Saturn likely moved slightly inward and then outward again, disturbing the orbits of countless planetesimals. This rearrangement explains patterns in the asteroid belt and the distribution of Kuiper Belt objects. During this dynamic period, Earth experienced heavy bombardment by leftover debris. This late heavy bombardment delivered additional water and organic compounds, helping set the stage for life. Some of the oldest impact craters on Earth and the Moon record this ancient era. The Moon itself preserves much of this early history. Unlike Earth, the Moon has no atmosphere or plate to erase its oldest surfaces. Rocks returned by Apollo astronauts show that the Moon formed when a Mars-sized object collided with the young Earth. The resulting debris coalesced into the Moon, locking in clues about Earth's early conditions. As scientists study exoplanet systems around other stars, they see similar patterns. Many young stars show disks of dust and gas, and some reveal gaps where planets have cleared paths through the disk. Observations of exoplanet systems with hot Jupiters or multiple planets in tight orbits suggest that planetary migration is common. These comparisons help test theories about what makes Earth's solar system unusual or typical. While many exoplanet systems host massive planets close to their stars, our solar system's arrangement of small rocky planets and distant gas giants creates stable conditions that allow liquid water to persist on Earth's surface. Comets and asteroids also connect the solar system's past to the present. Missions like NASA's Dawn, which explored the asteroid, Vesta, and dwarf planet series, and ESA's Rosetta, which visited comet 67P, show that these small worlds contain water, ice, organics, and evidence of past geological activity. Such discoveries deepen the link between primitive bodies and the conditions that nurtured Earth's early oceans and atmosphere. Understanding the solar system's hidden history clarifies how Earth gained its unique environment. It shows how collisions, migrations, and leftover debris shaped the conditions for life to begin. It also guides the search for other habitable worlds by highlighting which features stable orbits, a rocky surface, and access to water and organics are likely to appear elsewhere. The solar system's story remains unfinished. Ongoing missions and future explorations aim to visit more asteroids, return more samples, and map distant Kuiper Belt objects. Each discovery adds pieces to the puzzle of how planets form and evolve. As this history unfolds, one persistent question emerges: how does Earth's ever-changing surface continue to support life through time? And what hidden forces drive these changes beneath the ground? While Earth's inner heat drives the shifting of continents and the cycling of elements essential for life, another force shapes how humans understand the planet's place in the wider universe: the flow of time itself. For centuries, time appeared fixed and absolute. Newtonian physics described time as a constant backdrop, ticking steadily for everyone, everywhere. But in the early 20th century, Albert Einstein overturned this idea with his theories of special and general relativity, showing that time is woven together with space and is far from absolute. Special Relativity, published in 1905, starts with two simple postulates. The laws of physics are the same for all non-accelerating observers, and the speed of light in a vacuum is constant, regardless of the motion of the observer or the light source. These ideas lead to surprising consequences. Time does not pass at the same rate for everyone. When an object moves close to the speed of light, time slows down for it relative to a stationary observer. This effect, called time dilation, has been confirmed by countless experiments. One classic test involved extremely precise atomic clocks flown on airplanes. When compared to identical clocks left on the ground, the airborne clocks ticked slightly slower, just as special relativity predicts. This effect is tiny at the speeds of commercial jets, but grows significant as velocity increases. General Relativity, published in 1915, expanded this picture to include gravity's influence on time and space. According to general relativity, massive objects like planets and stars warp the fabric of space-time around them. This curvature explains gravity. Objects follow the curved paths determined by space-time's shape. The theory also predicts that time runs more slowly in stronger gravitational fields. This gravitational time dilation has practical consequences on Earth today. For example, the Global Positioning System GPS depends on satellites orbiting Earth. These satellites carry extremely precise clocks that must stay synchronized with clocks on the ground to provide accurate location data. However, satellites experience weaker gravity and travel at high speeds. Both special and general relativity affect the ticking of their onboard clocks. Without correcting for these effects, GPS locations would drift by several kilometers each day. Impact extends far beyond Earth. When astronomers study distant objects, they see time behaving differently on cosmic scales. Light from stars and galaxies takes millions or even billions of years to reach Earth. This means telescopes act like time machines, revealing the universe as it was in the past. The expansion of the universe also shifts light from distant galaxies toward longer, redder wavelengths, an effect known as redshift. Measuring this shift helps astronomers determine how fast galaxies move away and reconstruct the universe's history. Near extremely massive objects like black holes, general relativity predicts dramatic effects. Time slows almost to a standstill at the edge of a black hole's event horizon. This time dilation means an astronaut watching someone fall toward a black hole would see the person appear to freeze in place near the event horizon, while from the falling person's perspective, they would cross it without noticing anything unusual at that instant. Relativity's predictions hold up under the most extreme conditions yet observed. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow in the galaxy. M87, the shape of the glowing ring, matched predictions from general relativity, confirming the theory once again. Relativity also connects to particle physics and modern experiments. High-energy particles, called muons, produced by cosmic rays striking Earth's atmosphere, have very short lifetimes. Yet they are detected at Earth's surface because they travel near light speed, and time dilation lets them persist longer than they would at rest. This everyday evidence demonstrates relativity's role in the subatomic world. scientists continue testing relativity with ever greater precision. Instruments like LIGO detect gravitational waves, ripples in space-time, caused by massive objects like merging black holes or neutron stars. The existence of gravitational waves was a key prediction of general relativity, confirmed only a century after Einstein proposed it. Time and relativity reshape human understanding of how the universe behaves and how measurements on Earth connect to cosmic events. They show that time can bend, stretch, and differ depending on speed and gravity, and they guide technology used every day. These principles also open new questions. If time and space are flexible, what happens at the smallest scales where quantum physics rules? Reconciling general relativity with quantum mechanics remains one of science's greatest challenges, hinting at a deeper framework still waiting to be discovered. While scientists continue searching for a unified theory that links gravity with quantum mechanics, the universe offers visible evidence of how these forces shape matter's ultimate fate. Nowhere is this clearer than in the life cycles of stars, which reveal how matter transforms, recycles, and sometimes vanishes from view altogether. A star's life begins with hydrogen, the simplest and most abundant element, for millions too. Billions of years, nuclear fusion in a star's core converts hydrogen into helium, releasing energy that balances the inward pull of gravity. But this balance does not last forever. When a star exhausts its hydrogen fuel, its fate depends on its mass. Stars similar in mass to the Sun expand into red giants once they run out of core hydrogen. In this stage, helium fusion takes over, forming heavier elements like carbon and oxygen. The outer layers of the star puff outward, while the core contracts. Eventually, the outer gas shells drift away into space as a glowing planetary nebula, leaving behind the star's dense core, a white dwarf. A white dwarf is about the size of Earth but contains mass comparable to the Sun. Its matter is so tightly packed that electrons provide the pressure that keeps it from collapsing further. Over trillions of years, a white dwarf slowly cools and fades, becoming a cold, dark remnant known as a black dwarf, a stage the universe has not yet reached because it is still too young. More massive stars live shorter, more dramatic lives. When fusion creates iron in their cores, no further energy can be extracted through fusion reactions. Without outward pressure to counteract gravity, the core collapses in an instant, triggering a supernova explosion that blasts the star's outer layers into space. This explosion spreads heavy elements like gold, silver, and uranium across the cosmos. These elements enrich clouds of gas and dust, which can later form new stars and planets. In this way, matter cycles through generations of stars, building up the diverse elements found throughout the universe. The core left behind after a supernova can become a neutron star if its mass is below a certain limit. A neutron star is incredibly dense. Its matter is compressed so tightly that protons and electrons merge into neutrons. Just a teaspoon of neutron star material would weigh billions of tons on Earth. Some neutron stars become pulsars, emitting beams of radiation that sweep across space like cosmic lighthouses. Others exist silently, detectable only through their intense gravity or by the way they bend light from objects behind them. If the core's mass is large enough, not even neutron degeneracy pressure can stop the collapse. In this case, gravity overwhelms every force, creating a black hole. A black hole's gravitational pull is so strong that nothing, not even light, can escape once it crosses the event horizon. Black holes vary in size, from stellar mass black holes formed by single stars to supermassive black holes millions or billions of times heavier than the Sun. These giants sit at the centers of galaxies, including the Milky Way, where they shape the motion of stars and influence galactic evolution. Matter that falls into a black hole is thought to be lost forever from the observable universe. Although the exact physics inside a black hole remains one of science's greatest mysteries, theories suggest that information about this matter might somehow survive. But how it does so is still debated. Over cosmic timescales, the universe's stockpile of hydrogen shrinks as it is fused into heavier elements or locked away inside dead stars and black holes. Stars born in the distant future will have less fuel, and as existing stars burn out, new ones will form more slowly. Physicists predict a distant era when all star formation ceases and the last shining stars fade. White dwarfs, neutron stars, and black holes will dominate over unimaginably long periods. Even black holes lose mass by slowly emitting energy as Hawking radiation, eventually evaporating entirely. The universe's ultimate fate depends on dark energy, the mysterious force driving its expansion. If expansion continues forever, galaxies will drift apart until no light can bridge the growing voids. This scenario, known as the heat death or big freeze, would leave a cold, dark universe filled only with scattered particles and fading remnants of once bright stars. Another possibility is a big crunch, where expansion reverses, and the universe collapses back on itself, or a big rip, where dark energy grows so strong that it tears apart galaxies, stars, and eventually atoms themselves. Observations today suggest endless expansion is more likely, but questions remain about what dark energy truly is. The story of stellar life and death shows how matter constantly cycles through phases of creation and destruction, shaping the cosmos. As it evolves, each atom in every living being was forged in ancient stars that lived and died long before Earth formed. Understanding how stars end reveals how matter changes form but never disappears entirely. This cycle connects to the search for the universe's deepest laws, the quantum and gravitational rules that govern matter's smallest particles and largest cosmic structures. The smallest building blocks of matter behave according to the laws of quantum mechanics, but gravity's influence stretches across the entire cosmos. Bridging these realms has long been one of physics' deepest challenges. A key link came from Albert Einstein's theory of general relativity, which predicts that massive cosmic events send ripples through space-time itself. These ripples are called gravitational waves. Gravitational waves are produced when massive objects accelerate in certain ways. For example, when two black holes spiral around each other and collide, or when neutron stars merge. Unlike light, which can be blocked by dust and gas, gravitational waves pass through matter almost undisturbed. This makes them valuable messengers from places in the universe that would otherwise remain hidden. Einstein first predicted gravitational waves in 1916, but for decades they were impossible to detect. Their effects on space-time are extremely small, stretching or squeezing distances by less than the width of an atomic nucleus. Detecting such faint distortions requires incredibly sensitive instruments. This goal became reality in the early 21st century with observatories like LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO uses laser beams sent down to long tunnels arranged in an L shape. If a gravitational wave passes through Earth, It slightly alters the length of each tunnel. The lasers reflect back and forth, and scientists watch for tiny changes in how the beams interfere with each other. In 2015, LIGO made history by directly detecting gravitational waves for the first time. The signal came from two black holes merging more than 1 billion light-years away. This discovery confirmed a major prediction of general relativity and opened a new window for observing the cosmos. Since then, LIGO and its European partner Virgo have detected dozens of gravitational wave events. Many come from pairs of black holes merging, but one of the most significant detections involved two neutron stars. When these ultra-dense stars collided, they not only produced gravitational waves but also released light across the electromagnetic spectrum. Telescopes around the world observed the burst of radiation that followed, linking gravitational waves with visible signals for the first time. Such neutron star mergers explain some of the universe's heaviest elements, like gold and platinum. In the intense conditions of the collision, atomic nuclei smashed together, forging elements that later spread through space. This means the gold in a wedding ring or an electronic device likely originated from such a violent cosmic event. Gravitational wave astronomy allows scientists to study phenomena that would otherwise remain invisible. Black holes, for example, cannot be seen directly because they trap light, but their mergers send clear gravitational signals. These ripples reveal the black hole's masses, spins, and distances. Detecting gravitational waves also tests general relativity under extreme conditions. Each new observation checks whether space-time behaves as predicted when massive objects collide or distort their surroundings. The technology behind these discoveries continues to improve. New detectors in Japan, Kagra, and planned observatories in India and space like the European LISA mission will expand the search. Space-based detectors will be able to catch waves from supermassive black holes merging in distant galaxies, offering clues about how galaxies grow over billions of years. Gravitational waves could even shed light on the universe's earliest moments. Some theories suggest that shortly after the Big Bang, rapid expansion generated primordial gravitational waves. Detecting these ancient ripples would open a direct window to the universe's birth, revealing information hidden from ordinary telescopes. This new era of gravitational wave astronomy shows how cosmic signals come in many forms, not only light, radio waves, and X-rays, but also ripples in space-time itself. Together, these observations help piece together how the universe works at both enormous and tiny scales. With each signal, scientists gain insights into massive black holes, dense neutron stars, and the forces that shape matter and energy on cosmic scales. Gravitational waves connect relativity, quantum physics, and astrophysics into a single, expanding field of study. Yet many questions remain. What else might these faint tremors reveal about the hidden structure of space-time? And as detectors grow more sensitive, could they uncover entirely new physics beyond Einstein's theories, while gravitational waves open new windows on the universe's vast structure? Another frontier brings the focus back to a question as old as humanity. Is Earth the only place where life exists? The search for extraterrestrial life spans planets, moons, and distant exoplanets, blending astronomy, biology, and planetary science into one of the most compelling quests in modern science. For decades, Mars has stood at the center of this search. Early telescopic observations hinted at canals and possible signs of intelligent life, ideas that turned out to be illusions. Yet Mars remains a prime target because of its history. Evidence shows that ancient Mars once had liquid water on its surface, rivers, lakes, and possibly even shallow seas. Today, robotic missions like NASA's Perseverance rover drill into Martian rocks, seeking chemical signs of ancient microbes preserved in sediments. Alongside Mars, certain moons in the outer solar system have become promising candidates for life. Jupiter's moon Europa hides a global ocean beneath its icy crust. The surface shows cracks and ridges, suggesting that liquid water beneath might be in contact with rocky seafloors, providing the energy and chemistry needed for life. Missions like the upcoming Europa Clipper will fly close to this moon, studying its surface and environment in detail. Saturn's moon, Enceladus, offers similar intrigue. In 2005, NASA's Cassini spacecraft discovered plumes of water vapor and ice spraying from cracks near its south pole. These geysers hint at a subsurface ocean kept warm by tidal forces from Saturn's gravity. Samples collected from the plumes showed simple organic molecules, the basic ingredients for life. Future missions aim to fly through these plumes, again searching for more complex compounds or even hints of living microbes. Beyond the solar system, astronomers widen the search by studying exoplanets, planets orbiting other stars. Using telescopes like Kepler and TESS, scientists have found thousands of exoplanets, including some roughly Earth-sized and located in their stars' habitable zones, where temperatures could allow liquid water to exist. Detecting life from afar relies on searching for biosignatures, clues like specific gases in a planet's atmosphere that could indicate biological activity. On Earth, life produces large amounts of oxygen and methane, both of which could, in the right conditions, suggest a living biosphere elsewhere. Instruments on upcoming space telescopes, such as the James Webb Space Telescope and planned next-generation observatories, will analyze exoplanet atmospheres for these telltale signs. Radio telescopes also listen for signals that might hint at intelligent life. The search for extraterrestrial intelligence SETI scans the sky for narrowband radio transmissions that do not occur naturally. Although no confirmed signals have been found, each new advance in computing and telescope sensitivity makes the search more precise. Scientists also experiment with synthetic biology and extremophile studies to expand the understanding of where and how life might exist. On Earth, life survives in boiling hydrothermal vents, acidic lakes, deep underground, and frozen permafrost environments once thought too harsh to sustain organisms. These discoveries reshape the search, showing that life can thrive under conditions far beyond what was once considered possible. One major challenge is that even for distant exoplanets shows signs of water and suitable temperatures, confirming life requires careful study to rule out non-biological processes. Chemical reactions, volcanoes, or other natural processes can mimic some biosignatures. This means future telescopes must measure multiple indicators at once to build a compelling case. While no clear evidence of extraterrestrial life has yet been found, each mission adds knowledge about where to look and what signs to seek. Planned robotic explorers may one day return samples from Mars or fly beneath Europa's ice to probe its ocean directly. Discovering even simple microbes beyond Earth would reshape our understanding of biology, evolution, and humanity's place in the cosmos. It would suggest that life is not unique to Earth, but a possible outcome wherever conditions are right. The search for life unites questions about chemistry, geology, astronomy, and time. It demands patient exploration, sophisticated technology, and an openness to surprises that may challenge assumptions about how life begins and endures, whether scanning radio waves for distant signals or analyzing frozen plumes on a distant moon. Each step pushes the boundary of knowledge outward, while the search for life fuels curiosity about who might share the universe with humanity. Another set of questions reaches even deeper into the nature of reality itself. What is the true shape of the universe? What unseen forces control its expansion and ultimate fate? Modern astronomy moves steadily closer to these answers with technology that extends vision far beyond what the eye can see. The universe remains filled with mysteries. Dark matter holds galaxies together but cannot be seen directly. Dark energy pushes galaxies apart at ever-increasing speeds, yet its true origin stays hidden. Solving these puzzles requires observing the cosmos in greater detail than ever before. Today's telescopes already peer deep into space and back in time, capturing ancient light from billions of years ago. But new instruments are being built to go further. The James Webb Space Telescope, launched in the 2020s, offers a glimpse of this future. Its powerful infrared sensors see through cosmic dust, uncovering stars and galaxies that formed when the universe was young. Webb's early images reveal clusters of galaxies and the faint glow of the first light after the Big Bang. By studying these distant objects, scientists refine their understanding of how cosmic structures grow under the influence of dark matter and dark energy. Other telescopes push forward too. The Vera C. Rubin Observatory, under construction in Chile, will map the entire visible sky repeatedly, creating the largest ever time-lapse movie of the universe. By tracking the motion of billions of galaxies, Rubin will measure how dark matter shapes cosmic structures over time and search for clues about dark energy's behavior in space. Missions like the European Space Agency's Euclid telescope will soon join the quest. Euclid's goal is to chart the geometry of the universe by observing billions of galaxies, mapping their distribution in 3 dimensions. This giant cosmic map will help scientists test competing theories about what dark energy is and whether the laws of gravity change over cosmic distances, beyond dark energy and dark matter. Next-generation observatories will study black holes and neutron stars in unprecedented detail. The Event Horizon Telescope already produced the first image of a black hole's shadow. Future upgrades promise sharper views that could test general relativity in the most extreme conditions. Meanwhile, gravitational wave detectors will grow more sensitive. Space-based missions like LISA Laser Interferometer Space Antenna aim to detect ripples in space-time from supermassive black holes merging in distant galaxies. By catching these faint signals, astronomers hope to understand how galaxies and black holes evolve together and to look for hints of physics beyond Einstein's predictions. Radio telescopes, like the Square Kilometre Array, now under development, will scan the sky for faint radio signals from the early universe and possibly signs of alien technology. It will also explore how the first stars and galaxies switched on, ending the cosmic dark ages and lighting up the universe. New technology also brings the possibility of discovering unexpected phenomena. Each generation of telescopes has revealed surprises: pulsars, quasars, cosmic microwave background radiation. It is likely that new tools will uncover aspects of reality no one has yet imagined. These observatories do more than answer big questions. They raise new ones. How did the first black holes grow so large so quickly? Could the universe contain hidden dimensions or unknown particles that subtly affect cosmic evolution? Might dark matter be made of exotic particles that interact rarely but shape the universe at every scale? Such questions keep physicists and astronomers working at the edge of what is measurable. Future missions will not work alone. They will combine their discoveries. Data from radio, visible, X-ray, and gravitational wave observatories will be woven together, providing a more complete picture of the universe's structure and history. These advances also demand new generations of scientists, engineers, and explorers, designing and launching telescopes, building sensitive detectors, and developing algorithms to handle vast streams of data push human ingenuity forward. In this way, the quest for the universe's secrets shapes not only knowledge, but also technology and society through each new window on the cosmos. The universe reveals itself in sharper detail. It reminds humanity that every answer brings fresh mysteries and that knowledge is a horizon that always recedes as understanding grows.